Hello students, today we will solve the question paper of MSc, that is your third semester. Okay, so I will try to solve this question paper, and you can check this whenever the result will be out. Okay, so check this, and that will have the confidence, you will have the confidence for the marks what you get in the examinations. Okay, so this is what the inorganic paper chemistry for the third semester under general chemistry, uh, from the Karnataka University, Dharwad. Okay, and this is of the year 21, recent. Okay, 2021 March. Okay, now if you see here the questions here, so question number one, uh, and any four from the remaining. Okay, all questions carry each marks, and here the seven questions having 2 marks here, and one question is of 1 mark and 15 marks. This question one is, so in the question one you can see here they ask the Raka parameter R for this hexacyanocobalt. Okay, 3 minus is 462 per centimeter, while that for hexamine cobalt plus 3 is 612 per centimeter. Account for this difference. Okay, so this is the first question. So he has asked for the Raka parameter, and he has said that for cobalt, both are the cobalt complexes here. Okay, so both are cobalt complexes of plus 3, one amine complex and one cyano complex, and one is having the cyano complex, cobalt plus 3 of cyano complex ligand. Okay, so of cyanide ligand, so it is having 462 per centimeter. This is a Raka parameter, and that of amine NH3 ligand. Okay, so it is having 612 per centimeter, and you have to comment on this. Now what is this Raka parameter? So this is, you have to see first. So this happens when the atom has more than one electron. Okay, so when the atom has more than one electron, so as I said the class, that there will be a electrostatic repulsion, okay, between these electrons. So there will be some electrostatic repulsion will be there between these electrons. And this Nephelosatic effect, this refers to the decrease in the Raka interelectronic repulsion. So this Nephelosatic effect, that is called this repulsion, so that is Nephelosatic effect. We call it as a Nephelosatic effect. Okay, and this effect is referred to the decrease in Raka interelectronic. This refers to the decrease in the Raka Raka interelectronic repulsion parameter. This is what Nephelosatic effect. This is termed with the decrease in the Raka parameter. Okay, and this decrease in the Raka parameter is indicated by the term B. Okay, B indicates that in a complex there is less repulsion between the two electrons. Okay, so this indicates that there is less repulsion between the two electrons in a given metal uh, d orbitals. Okay, then the respective metal ion in gaseous metal ion state, and this implicate the size of the orbital is large in the complex. Okay, so what this implicate, the size of this mainly indicates the size of orbital is very large. That's called cloud expansion sometimes. Okay, so this is what the effect is here, and the effective positive charge here, what happens, the effective positive charge on the metal will decrease, is decreased in this case. Okay, and because the positively charged on the metal is reduced by negatively charged ligands. Okay, the positively charge of the metals is reduced by the negative charge of the ligands, so this effect is there. The d orbitals will expand and they form the covalent bond. Okay, so d orbitals expands and they form the covalent bond here. So that is the reason. So you can see here the cobalt cyano complex, you are having the less here, uh, the next less parameter here, whereas in here amine complex you can see here is having more. Okay, that means in this you can see that whatever we have explained here now, that is the interelectronic repulsion between the two electrons whenever there is more here. Okay, so it will happen that the decrease in the Raka parameter B indicates. So this is what happens here. So here decrease in the Raka parameters. Okay, so this is important, decrease in the Raka parameter B, and in the complex here. Okay, so that indicates there is less repulsion between the two electrons here. So here there is a less repulsion here. Okay, and you can see that that's why the Raka parameter is decreased here, but the interelectronic repulsion in the second complex having the amine ligand is more here, and that's why you can see the Raka parameter here, it is more. Okay, so this is what about you have to explain. Okay, I have told in the very broad way, but in two very simple way you have to explain this. Okay, and it all is works on this Nephelosatic effect here. Okay, so this is called as Nephelosatic effect, or sometimes it is you have to explain this in the terms of the size of the orbitals. Okay, the size of the orbitals and the ligands, approach of the ligands. Okay, so this is how you have to explain this question 1. Mainly you have to explain with respect to Nephelosatic effect as well as the interelectronic repulsion, and if required you can explain with respect to the what I say, the metal decrease in the positive charge of the metal. Okay, metal by the negative charge of the ligands. Okay, so the d orbital expands and they form the covalent bond. So something, so you can found you can write this, but if you add these 2 points, that is more than sufficient for 2 marks. Okay, and if you add some extra points like what I said now, so that will be helpful for the addition of some good impression. Okay, now we will see the second here, that is calculate the spin only measure magnetic moment for hexacyano. Okay, so this is hexacyano for it 4 minus, and hexaaqua cobalt complex plus 2. Okay, so this is second. So here there is the spin only magnetic moment is asked here. Second question, spin only magnetic moment, magnetic moment. So you know the it's very simple question. So this is what he has been asking. So Fe Cn6 4 minus. Okay, Fe Cn6 4 minus. Okay, so the formula for this you know is very simple. Spin only, that is mu s spin only, that is root of n into n plus 2. Okay, so this is what you have to write, where n is nothing but number of unpaired electrons, and you have to see here iron is in plus 2 state here. This is 6 and this is 4 minus, so here Fe is in plus 2 state. So plus 2 means it is in d6 configuration, and d6 means what? 1 2 3 4 5, 1 2 3 4 5 6. That means 4 unpaired electron is there. So if you put this 4 unpaired electron under the root system here, 4 root of 4 into 4 plus 2. Okay, that is equal to root of 4 plus 2, 4 5 6, 6 4 are 24, root of 24. So 4 4 are 16, 5 5 are 25. So something it comes around 4.89 Bohr magneton. Okay, if you see this 24 square, so it falls between the 16 as well as 5 5 are 25. So something 4.89 Bohr magneton will be the answer. And if you see this next, what he has asked for the I think cobalt plus 2. Okay, which is a d7 system. So 1 2 3 4 5 d7, you know, so you can put it like this: 1 2 3 4 5 6 7. That means 3 unpaired electrons. Again same thing, you can write here 3 into 3 plus 2, that is 3 4 5, so 15. So root of 15, so it comes around 3.87. So 3 3s are 9, 4 4s are 16. Yeah, so near to this, so 3.87 something you come here Bohr magneton. So this is what the answer. you can have for this question here. Okay, so next, if you see, the next question in this paper is explain trans effect with example. So this is very simple here. So you know what is trans effect. So any ligand which is having what you say, the uh, effect of having this uh, having this ability to place the another ligand trans to itself, so we call that effect as a trans effect. Okay, any ligand having the ability to place the incoming ligand. So if I put this incoming ligand, and if this ligand, if any of the ligand of this four having the ability to place this incoming ligand to trans to it. Okay, so like this, if it is like this A, then that I can say that out of these three ligand, 1 2 3, the second ligand has a better trans effect than the compared to the 3 and 2. So this is what I can explain with the trans effect here. And the best example, and you know that trans series is there, where the cyanide, then carbon monoxide, and nitric oxide, C2H4 ethylene. So they are having the highest trans effect. If you find this ligand, so these are the ligands. If C2H4 ethylene, as we have discussed this in the class, that if this is C2H4, and if Cl, you take another ligand, when Cl is entering here, and these are the different, you take it as any of this ligand, like Br, something like that. Here also Br, here also Br. Okay, and here also Br, and C2H4 here, this ligand. So C2H4, when chlorine is inserted in here, so C2H4 will have the better ability than Br to place this Cl minus here, opposite to here, like this. Okay, so Br will go and Cl will come here. So because this is having more capacity than Br to replace to place this Cl to transposition to itself, and that's we call it as a trans effect. And if you see the cyanide, carbonyl, nitrosyl, ethylene, okay, so ethane, so this have the more ability to place this incoming ligand to trans than compared to the, as I said here now, bromide, chloride. Okay, and then pyridine, then here comes something nitrogen, and the final you can see the weakest is your H2O. Okay, so this is what the most example they are you can explain for the trans effect, taking this ethane molecule or nitrosyl or carbon monoxide or cyanide, so and explain this effect by taking any of this. Best example you can give it of cisplatin. Okay, so this example you can give for the 2 marks. Okay, so this is how we can explain for this question number what is that, that is your trans effect, third question number. Okay, so now next we'll go for mention biological role of hemocyanin. So what is this hemocyanin? Biological is very simple here. So hemocyanin, biological role of hemocyanin. Okay, so what is this biological role of hemocyanin? So hemocyanin, first you should mention that it's a protein having the copper. Okay, it's a protein having the copper, and it has the capacity to bind and transport the oxygen like hemoglobin does in human beings. Okay, so this also binds the oxygen and it transfers in mostly in arthropods. Okay, so mostly in arthropods and molluscans. Okay, so mostly marine. This one you can see this hemocyanin is present in this species. Okay, and it's a respiratory protein, you can say, and the name itself says it's a non-heme actually, and it's having blue in color. So it having the blue color, and that's why blue protein also sometimes it's called, and having the molecular weight along the crores. So in crores you can see its molecular weight will be there. And if you see it is having the structure of having the copper plus one state. Okay, having three histamines amino acids here, bound with three histamine amino acids here, and you can see like this copper one state, and you can see it is having the three histamines structure in this way. Okay, and when it is uh, binding here with oxygen, so you can see here, so this copper is going to bind with some like this in this way. Okay, copper something bridged like this. Okay, and you can see here three amino acid structures like this. amino acid of histidides like this, and it is binding oxygen in this way. Okay, and here copper will be in +2 state. So here it is in +1 state and here it is in +2 state. Okay, so diamagnetic, and here you can see it is in antiferromagnetic. +2 state, it is in antiferromagnetic, and here you can see it is in +1 state, usually diamagnetic in nature. Okay, so this is what about the hemocyanin. So if required, you can explain with this what is the structure if required. Otherwise, if you explain what I had told here with points also, so you will get 2 marks. But if you present like this, so it's better for the impression, okay, in the further scoring good marks for the further points, or seeing this only you will get the full marks. So list left to you. Okay, so this is what about the hemocyanin. Next, we can go for the next question, that is the IR spectrum of the XY2 molecule gives two prominent signals. Predict the structure of the molecule. So it is totally depends on the molecule here. XY2 he has given, and you have to predict the molecule, and he has given the IR frequency. Okay, so here it's a broad concept of IR. 2 marks is been asked here, but this all depends on the frequency, mode, and all. So you know that for non-linear, okay, for non-linear, the number of vibrations, total degree of freedom, it is 3n minus 6. Okay, mode of vibrations. And for linear, so you know this, that is a 3n minus 5. Okay, so there will be translational, rotational, vibrational, these all things you know. So there will be translation, rotation, vibration, mode of vibrations. Okay, degree of freedoms, and this is what. Okay, so you can see the linear molecule, so there are 2 transition, rotational degree will be 3. Okay, so 3n minus 5 is, and for non-linear you can see the translation will be 3 and the rotational will be 3. So that for the vibration will be 3n minus 6. Okay, so here for non-linear, okay, 3n minus 6. So translation vibrations will be here 3, rotational will be 3. So okay, that's why the total vibrational that will be 6, that is 3n minus 6. Okay, so this is what usually it starts in this way, but this is not required for to write this. Okay, this all parts here. Now thing is what, so there are, so it's very tricky here. So you can give the question, we can explain this with taking the CO2 also. Okay, so CO2, so in this you require to know about the, what to say, the PQR bands also, PQR. Okay, so this also comes in this IR spectroscopy with respect to this PQR bands here. Okay, and if you take the band molecules, okay, so SO2, okay, where you can see here, so non-linear SO2. So here the PQR, all 3 modes are IR active here. So if you see PQR here, all 3 modes, whatever we are going to get here for non-linear, are IR active. Okay, they are IR active. Symmetric, asymmetric, and bending. Okay, what are the 3 modes means? Symmetric, asymmetric, and bending. Symmetric, asymmetric, and bending mode. Okay, so all these 3 modes in this non-linear SO2, so they are IR active. Definitely we know that, and they are PQR. Okay, they show this signals. Okay, so this is what, and usually if you see the carbon monoxide like this. Okay, so in this carbon monoxide, you are having usually they have the axis of symmetry here. Okay, they are having the axis of symmetry here, and this have only the PR bands. They have the PR bands. Okay, the only PR bands, and the bending mode you are having of this, whenever, because they are having the stretching frequency, asymmetric and symmetric stretching frequency, and sometimes they have also the bending mode like this. Okay, and if you see this bending mode of this carbon monoxide, so you can see this, they show the PQR branch. They show in the PQR branch. Okay, the bending mode usually they show in the PQR branch, and the PR, they are only for the linear molecules. So PR only for the PR, they are only for the linear molecules. Okay, and the bent mode, usually they have the PQR contour. Okay, PQR contour. So this we can have this, and usually and the best example to show that uh, the what you say the prominent peaks, showing for the both this now with respect to this PR and PQR, like this is important now. Okay, because what does the question is here. So let me see the question here. Where is the question paper? Okay, so let me see the question here. So whether the signals is being asked here, so that is important to be noted here. Okay, so we'll see here. Let me see. So what is that here? IRXY to give two, yes, very correct. So here two prominent, so see here, so gives two prominent signals. Two prominent signal, this is important. To two prominent means you can see that it should be lying in the two contour layer, that is one is PR and one is PQR. Okay, and you know that we have taken the mode of SO2 where all the modes will be PQR IR active, and we have taken this CO2 where the showing the PR bands only for the linear structure here. Now if you take the structure of N2O nitrous oxide, that is NN in this way. Okay, N2O. Okay, so this is a molecule usually asymmetric. They have the better asymmetric okay, asymmetric mode, stretching and bending mode. Also you can see here asymmetric stretching and bending mode for this nitrous oxide N2O. And you can see, so they are having the two prominent come in the region of two prominent, that is two of PR region, and they are showing one PQR. Okay, so this is how we can show, and we can represent this as a B and A here, like this. Okay, so nitrogen and oxygen in this way. Okay, so this is what we can say. So at the most you can represent this molecule having the two prominent signals here. So that is one for the PQR contour and one for the PR, okay, branch, I can say. And this is depending on the symmetric nature of the molecule. Okay, so bending mode, stretching mode, and symmetric asymmetric bending, these all things, and in which branch or which this they are going to fall. Okay, so this is the more important here. So the symmetry plays a very much important role in this question here. So you should know the molecular plane exists or not, symmetry of the molecule, or you have to see that whether that is infinity, or you should know that the symmetry, what is the infinity H or CS. If you take bent mode like H2O, C2V group. So this all group theory knowledge is very much important to answer this. Apart from this two range of the IR mode here, that is branch falling here, that is PR mode and the PQR mode for the bend and the stretching frequency. Okay, if it is symmetric or asymmetric or bending. So if you have this, so definitely you can see this. And if you see that carbon dioxide, as we have explained here, CO2, which is having the linear, so definitely, so you can see for this CO2 also. Okay, so you are going to get the two peaks usually prominent. We are going to get two peaks as we had explained now. So that is because of asymmetric stretching. Okay, and particular wavelength, you can see one very eminent peak you can going to get here. So at particular this one, because of the asymmetric stretching, and the second at somewhat lower side at around 600 per centimeter something. Okay, so you are going to set the get the peak here because of the bending mode. Okay, so vibrations, so like this, you can see that even the CO2, if you see the spectrum, you are going to get the two dominant peaks here because of the bending as well as the stretching mode. So this also, if you mention, so no problem. This also, as I said, N2O, so no problem. Here also you are going to get the two prominent peaks here. Okay. So totally, there should be the, you should have the knowledge of the what you say, the branches here. Okay, so contour branches. So that is what the PR branches we say. Okay, so somewhat it is PR branches. So somewhat it is like this something. So it comes in this way, like this. It will be shown. So this is what about the P, and this is what about the R. So PR branch you can say. Okay, and if you see the PR branch of CO2 here, so for carbon dioxide, so parallel vibrations for this is you can see the parallel vibrations. Okay, so you can see the PR usually. Okay, so parallel vibrations, so it comes under PR, and for PQR branch transitional, okay, perpendicular vibrations from the axis. Okay, for the for usually for the non-linear only. So if there is a non-linear only, you can see this PQR mode of the vibrations you can see here. And usually this is referred, PQR is usually referred for if the delta J, for if it is -1, so you termed as a P here. If delta J will be the +1 R, and if delta J is equal to 0, it is Q. So this way it has been represented. Okay, so in this, okay, so vibration, so here middle place, that is where the G is equal to 0 will be there, and here there will be some, that is PQR, like this. Okay, so this is P and this is Q and this is R, like this. Okay, so this is Q, okay, usually, and this is P and this is R. Okay, always. So Q always it will be 0. So this is what about the, you can say. And if he is asking for this structure predictant, you can give maybe this B like this. This is, and as I said now, so these are the different modes now. So this may be like this, or BAB. This may be in this molecule, or BBA. Okay, so like this. So these two are more preferably, as I said here. So anyway, so you can give the example of CO2, you can give N2O. Okay, so this is what you can show some examples in this way, and you can explain this mode of linear mode, or with respect to this PQR mode. Okay, so PQR, this one, I think this is more than sufficient here. Okay, symmetric, symmetric, and this vibrations is more important here. So any students have explained in this way with having some of the points included here in this. So definitely you can have some marks here. If any extra other examples also comes here, no problem. So you are going to get the marks, but pertaining to the symmetry. So you have to be have the correct symmetry and group theory knowledge for that molecule. And with respect to, as I said now, the PQR mode branches, so where which is the relevant for this particular, you can say, what is it, from signals. Okay, so how we, because some of the molecules they have only PQR as bending modes, as I said, so only one signal you are going to get. Okay, so like this, some molecules may be prominent for the two signals, like it may be for the bending mode at some lower this one, and for signals, and for the stretching higher signals, similar like this too, like in carbon dioxide we have seen, or N2O, NNO. Okay, so you can see in that also, so two prominent signals. So like this, so in this way you have to explain this IR of XY2 molecule and two prominent signals. So this is very tricky type. So this is what okay, fine. So if you have understood in the this one IR in basic thing also, you can explain with this, and we will see that. Okay, so this is, but with respect to this branches and all, it's better to better answering will be there for this question. Okay, with example, with symmetry, and with the structures. Okay, so next we'll go for here. So indicate the different ways of coordination of nitrates. Okay, two metal ion and the resultant symmetry in each case. So it has been asked for the nitrate ions. you see here different ways of coordination of nitrate to metal ion. Nitrate means what? NO3. Okay, nitrate ions to metal ion M plus. So this is what been asked. And free nitrate, you know that it is having the single band at our D3H mode. Okay, if you see the nitrate ion like this, okay, free nitrate ion having the negative charge here, NO3 minus. So like if you see the BCl3 like this, so this having something like here having the C3 axis, okay, you know that, and having two axis also, 3C2 axis. Okay, C2 axis, if you rotate this like water molecule, you can see it is coming on the same. So 3C2 axis, and along with the 3 sigma V and sigma H. So these are the four modes of the degree of group here, groups here, okay, of this molecule, that is uh, nitrate here, and having this structure of trigonal planar, and it is having sp2 hybridization. And what you see here, so it is having the D3H, okay, just in the free point group with having the free in the free nature, like in sodium nitrate NaNO3 sodium nitrate, okay, and having the single IR band here. So you can see the single IR band also you can get in this molecule. So this is what about the what you see the single the nitrate molecule here, okay, ligand here. And you can see upon coordination of one of this now here, so upon coordination of one of this to the metal ion oxygen here, the symmetry is lowered now here, and it is converted to C2V like water. Okay, so from D3H, so you can see that the symmetry is lower to C2V now nitrate, and you can see that two different bands is got now here. So because of lowering here, one of the oxygen is bonded to metal here, symmetry is lower to C2V from D3H, and you can see here, so two band, from one band you can going to get now two bands here, IR bands. Okay, so two different bands at nearby ranges. Okay, nearby ranges. So two band is more than sufficient. No need to mention that 1400 or 1200 something like that. Okay, so 1460 or 1280 centimeter something like that, no need, but two bands is going to observe here. Okay, so this is what you can explain for the question here. Okay, so what happens for the nitrate molecule? So this is it. Okay, so I hope you got this also here. Then next is the state the conditions required for the samples to be satisfactory for NQR study. See, okay, so state the conditions required for a sample to be satisfactory for a NQR study. So conditions required is asking for NQR, that is nuclear quadruple resonance satisfactory state. So conditions required for the sample to be in NQR. So you know that what the molecule should have the magnetic dipole moment. This is what quadruple, this name itself is there, quadruple. So the molecule should have the dipole moment, that is your quadruple moment usually. Okay, they should have your have the molecule should have the magnetic dipole moment, quadruple moment, and this leads to the magnetic electrical asymmetric electric charge distribution, okay, which is leading for the asymmetric electric charge distribution, and should be in a diamagnetic, okay, nature, unpaired electron nature should be there here, and solid substance usually, definitely there should be solid substance. Okay, solid substance should be have the quadrupolar nuclei. Okay, so they should have the quadruple nuclei, and it is detected by the radio frequencies used here. Okay, and you know that the nuclears with spin greater or equal to 1. Okay, so such as you can see nitrogen greater or equal to 1 nuclear spin. So example, you can give nitrogen 14, okay, chlorine 35 like this, or copper 63, so like this. Okay, so these are some of the you can say the conditions for the NQR. Okay, so this is what you have to explain, and diamagnetic nature is very much important, because you know that unpaired electron, that will affect the relaxation time of the nuclei. So this is what some of the what do you say, the the nature or the conditions required for the NQR. So some 2-3 points if it is included there with this active nuclei of NQR, so you are going to get the marks here. Okay, next. Now the last question here is explain the fact that the EQQ chlorine in BrCl is minus 103.6 mHq, and whereas that of KCl is nearly 0. The KCl is nearly 0. This is also very tricky, very depth means NQR, in NQR only it will come here. So KCl, the EQQ value is 0, whereas in BrCl, bromine chloride, okay, so you can see that it is having some negative value. Okay, so this has been asked. Definitely it is some ionic nature here, so always if the electron environment around the nucleus, okay, so if you see the electron environment around the nucleus, in spherical, okay, Cl, KCl, Cl minus always, because of pure ionic in nature, you can see here the Cl minus will be there, purely ionic in nature. So because of the spherical, now here what happens here, there is a spherical will be more, spherical nature will be more in this ionic bonding here, and you can see the all nuclear orientations are equivalent here, okay, in this molecule, and correspondingly the quadruple energy states are in degenerate here. So if you see here, the quadruple energy states will be degenerate, having same energy, will be in degenerate, that is having the same energy, and for which you will get this I value, that is nuclei value here is equal to 0 or 0, or if it is half also, you can see here that the quadruple, if you see there is no quadruple energy state here, so there is no quadruple level here. So if it is a 0 here, okay, so because of the spherical nature of this electron distribution, so there is no electric charge asymmetric distribution. So you can see that when there is no this electric asymmetric distribution, so I will be 0, and when I will be 0, so there will be no quadruple energy state, and that's why so KCl always have 0 EQQ value, which shows that it's pure ionic nature, and the pi bonding, usually pi bonding S and D hybridization. So if you find this S and D hybridization, so it's not possible to interpret the EQQ value. Okay, so whenever there is pure ionic in nature, whenever there is pi bonding nature, and whenever there is S and D hybridization, okay, wherever you see this, it is very difficult for the, it is not possible to interpret the EQQ value. Okay, so this is what, but however in BrCl you can see, so there is some covalency nature is there, so there is no the pure ionic nature here, and that's why definitely you are going to get very low EQQ value, distinct EQQ value here. So that's why this is a reason why the BrCl is having minus 103 megahertz, okay, value, whereas KCl is nearly 0. Okay, so this is what with respect to the spherical nature of the nuclei and ionic and covalent bonding of the molecule. Okay, so usually the asymmetric electric charge distribution is very much important. Okay, hopefully, so I think for this is very much important to pass now in this examination in third semester. If you have qualified these 7 questions here with 2 marks, at least 15, at least 8 or 9, definitely in the descriptive answering, so you may answer definitely and you are going to clear this paper. Okay, so only thing is what, this first part is very much important, and I have told you. Okay, so this if is there, so Raka parameter, definitely Nephelosatic effect, interelectronic repulsion, these 2 words should come here, and B value, so B value will be lower, so interelectronic repulsion will be less. So this is what you have to explain. Okay, so what is this Raka parameter and Nephelosatic effect, and decrease in the B factor, so decrease in the B factor, so that thing you have to explain, and because of the less or more interelectronic repulsion. Then spin only magnetic moment we have done, the root of n into n plus 2, so d6 d7 system is there. Trans effect we have explained this also with cisplatin, you can explain it here. or you can explain this with any of the example, as you know, but having this having taken the very great effect trans effect ligands like nitric oxide NO or C2H4 ethane, or some as I have given carbon monoxide, so that you can take and explain this. Then biological hemocyanin, you can definitely, structure is given very good. Copper 1 to copper 2 state, diamagnetic to antiferromagnetic state, you have to explain here. And main thing is mode of transportation of the oxygen here as hemoglobin, but this is in blue in color, so it is also called as blue protein. But since though it is written as hemocyanin, but it's a non-heme protein, so this is how we have to explain this. Higher spectrum, definitely XY2, so you can give, let me see, so it's left to your intelligence here, so which example you give, because in the class I don't know whether we have whether you have come across this PQR here, but anyway, if you give the if you give some of the examples of linear, non-linear, and explain that with respect to some, and if in your example it comes like which is related to the symmetry as well, and the contours like PQR, okay, PR and PQR signals type explanation, so definitely if CO2 is there or N2 is there, some examples not like SO2, okay, SO2 if you have written this, then definitely some problem will be there, because SO2 is going to show only one band, that is PQR. So we have to see this, okay, so so depends on the examiner and the example what you have given, okay, so it depends on that, okay. So this one, so CO2 N2 is there, then definitely you will be relaxed, but some other examples are there, so we have to see the see the group theory of that example, and you have to see whether that molecule is going to show the two significant indications with respect to the PQR and PR range. Okay, so this we have to see in this. Next, indicate the difference ways coordination of nitrate. Definitely nitrate have shown the D3H, okay, in the free state like sodium nitrate, that you have to explain D3H with having the four point groups here, so that is order of the group here. And then you have to show that showing single band here IR, and when it is bonded with the metal ion, any metal ion here, then that will be reduced, point group will be reduced from D3H to C2V, okay, and you are going to see two bands. So this is how the change will be occurred when the coordination of the nitrate with the metal, so this you have to show clearly. Then conditions required for the sample to be satisfactory for NQ residue, that it should be solid in nature, it should have diamagnetic in nature, and it should be having the quadruple nuclei, so that is very much important. So asymmetric electrical spherical symmetric electrical, this should be distribution should be there in this NQR. Then last one, that is what explain the fact that yes, definitely chlorine BrCl2 and KCl is 0, because what of the ionic in nature, so Cl minus, absolutely the symmetric spherical nature electrical distribution will be found in the chloride, and that will have the electrical distribution equally symmetrically equivalent, and that's why so quadruple moment is lost here, and that's why nearly 0 we can see, or 0 we can see for the KCl, whereas in BrCl you can see in covalency nature, and that's why definitely there will be some electronic asymmetric distribution across the nuclei, and that's why the quadruple nuclei is going to form here, and that definitely is going to show some significant values here, negative value here in megahertz for this BrCl. So this is what, okay, and definitely yes, I think this is what about the 2 marks questions. If you are explained in this point, so definitely it's very good, okay. So just judge it how you have explained written this, and based on that you can mention the marks here, how much you get. And if you are scoring well here out of 15, well here by 7 to 8 marks at least, so then definitely there is a chance of passing here, okay. At least 10, about 10 means you will score good, okay. This is your passing tendency. But if you fail to get marks here below less than 5, then definitely the whatever the further questions will be there here, the descriptive here, so I don't say that you are going to get good marks. You may pass to the edge, but failing also is more possibility is there. So only thing is if you score here, definitely you are going to get about 10 means definitely you are going to get good marks for letter. Below 10 means okay, below 5 is very risky, yes, okay. Next we'll go for in the next video, we'll solve for the next descriptive type of solutions, okay. Thank you.